For decades, particle physicists have been puzzled by a simple but stubborn question. How do some of the most fragile atomic nuclei survive the most violent conditions in the universe? Now, scientists at CERN believe they finally have the answer. Working with the ALICE experiment at the Large Hadron Collider, an international team led by researchers from the Technical University of Munich has solved a long-standing mystery in particle physics. They've directly observed how light atomic nuclei and their antimatter counterparts are actually formed in extreme particle collisions. The stars of this discovery are deuterons and antideuterons. Each of them is made of just two particles. A deuteron contains one proton and one neutron, while an antideuteron is made of their antimatter equivalents. Because they're so simple, these nuclei are perfect probes for studying the most fundamental force inside matter, the strong interaction. The strong interaction is what binds protons and neutrons together inside every atomic nucleus. But here's the puzzle. At the LHC, protons collide at nearly the speed of light, briefly creating temperatures more than 100,000 times hotter than the center of the sun. Under such extreme conditions, delicate objects like deuterons should instantly fall apart. Yet, for years, experiments kept detecting them. So, how do they survive? The new measurements reveal a surprising answer. Deuterons are not formed at the very beginning of the collision. Instead, the protons and neutrons that make them are produced later, emerging from the decay of extremely short-lived, high-energy particles known as resonances. Only after the collision starts to cool do these particles combine into light nuclei. In fact, about 90% of all observed deuterons and antideuterons are created through this delayed process. They form after the chaos settles, when conditions become cooler and calmer. According to Professor Laura Fabbietti of TUM, this discovery is a major step toward understanding the strong interaction. It clearly shows that light nuclei don't form in the hottest phase of a collision, but later when the environment allows them to exist. And the impact goes far beyond the laboratory. Light atomic nuclei also form naturally in space, especially when cosmic rays collide with interstellar matter. They may even help scientists search for signs of dark matter. With these new results, researchers can now build more accurate models and interpret cosmic data with greater confidence. At the center of it all is CERN's Large Hadron Collider, a 27-kilometer underground ring on the border of Switzerland and France. By recreating conditions similar to those just after the Big Bang, experiments like ALICE allow scientists to study matter at its most fundamental level. In doing so, they're not just answering old questions, they're helping us understand how the universe itself came to be. And sometimes, solving the biggest mysteries starts with the smallest nuclei.